Hello everyone, this is Sai Tariq. I'm doing my master's program in computer structural engineering at Mahindra University. As a part of my curriculum, I'm doing a project on comparing and monitoring a chloride-induced corrosion resistance of different types of steel rebars using piezoelectric sensors. Behalf of the course Infrastructural Health Monitoring under the supervision of Professor Visalakshi Tatakola. So, uh, so we know that the reinforced concrete structures are they are currently used widely around across the world. So even the steel bars are embedded inside the concrete. Even it can easily get affected with the aggressive agents if the concrete is permeable, and even that corrosion can affect the concrete to deteriorate. This cause some incipient damage in the structures. So it uh, it will it will leads to the spalling of the structures. So spalling of the concrete cover in order to avoid that and to to aware when the material is the steel is going to corrode beforely, we are monitoring it in a continuous way so that we can clearly we can get to know when the corrosion is going to initiate in a steel. So objective of the project is to compare and monitor the accelerated chloride-induced corrosion of different types of steel bars and to yield which type of steel bar is recommendable and which has the highest resistance to the corrosion. So in this project, I have taken chosen the three types of steel rebars. So first one is the plain forged steel, and then TMT, and then epoxy coated. So as per the ASTM standards, so 16 diameter bar is used for this corrosion monitoring. So first we have done the isolated corrosion monitoring for bare steel bars, and then the same steel bars we are embedded in the concrete cylindrical prisms. So after without cover, how much time is it? How does the steel bar corroding, and with concrete cover, how the steel bar is corroding when it is exposed to the environment of chloride induced corrosion, and then the difference in the data are calculated and acquired and analyzed by RMST tools. So these are the specimen I have adapted for bare rebar accelerated corrosion for each mild plain bar and the TMT bar and epoxy coated bar 1, and for the each concrete system for 1. So whichever you are seeing is the free PZT sensors surface mounted on the rebars. So PZT sensor is the one which act as a both actuator and the sensor. So in the PZT sensor, we will input the electrical signals that will may convert that as a actuator. It will convert that into the mechanical stresses, and through vibration it will give the mechanical stresses to the structure. And when the electrons are passing through the piezoelectric sensor, when the electron surface waves propagates from the PZT sensor, the conductance of the material will disturbs that electrical propagation. So that in that sense, how much it's a disturbing that will sense, and it will that electrical through that mechanical that it will give again the conductance data of that material. From that conductance data of the material, we can qualitatively say that the from the structural peaks how much it is getting deteriorated, or does the structure is getting damping, or it is getting deteriorated or what. So you can see as in the first image, free PZT sensors are soldered, and then housing preparations are done at the TMT bars, epoxy coated and plain bar, and then the PZT sensors or patches are bonded using epoxy, and then again the over the layer of PZT sensor epoxy coated is done. So these three layers are three bars are immersed into the brine solution, that is nothing but the NaCl solution containing 3.5% of concentration. So here we are we are making an electrolytic cell. So because to accelerate the corrosion, that should be a potential difference between the two materials, the chemical reaction, electrolyte chemical cell reaction to happen. So here we are making the three rebars, whichever we are going to corrode as an anode, and a copper bar it act as a cathode, and the cathode is connected to the negative terminal of the voltmeter, and the other three bars which rebars which act as anode are connected to the positive terminal of the voltmeter. So in order to maintain the potential difference over the throughout the experiment, we have maintained the 5 voltage potential difference throughout the experiment. So you can see this is the experimental setup, and this is the vPro software interface where we can get the structural conductance and the susceptance. So this is the vPro software, and this is the LCR meter, which gives the conductance and electrode susceptance signal. And this is the voltmeter I was talking about. The LCR meter to acquire the data, and voltmeter is to supply to maintain the constant voltage difference, potential difference between the bars. So this, as I saying, for the actuator action to happen, so piezoelectric sensors need that need to generate some electrical mechanical stresses. So that in order to create that mechanical stresses in form of vibration, we will give the 30 kilohertz to 400 kilohertz frequency with the step count of 100 kilohertz. And so this is how the experimental setup goes, and we can see that LCR meter. It is connected to the PZT sensors, and the LCR meter is also connected to the vPro software interface through any computers, so that we can acquire the data of conductance of the structure of that material or the element whichever the PZT sensor is bonded to, and the susceptance is to diagnose the PZT pads whichever you are using, that gives the health condition of the PZT sensor. So if this setup was totally made for 38 hours, we have continuously monitored. In that first 10 hours were done for 75% immersion. At the frequency of each 1 hour, we acquired the data, and then after 10 hours, we can the immersion percentage of the water percentage immersion is reduced to 50%, and for the next 28 hours, for each 4 hours, the data has been acquired. Throughout the 30 hours, the potential difference maintained was 5 voltage. And these are the initial masses of the rebars that you can see for the plain forged bar and the TMT bar and the epoxy coated bar. So these are the initial masses. So for each hour data, these are the data acquired. These are the conductance signals of the structure. For example, say this is the plain rebar signals, conductance signals. You can see the dark black one is the baseline healthy state signal, and 38th one is the 38th hour signal is the red one. You can see there is a shift in peaks, and there is some excitation in the signals. This indicates that there is a loss of stiffness, or we can tell that has the dampening the stiffness as before has been, whichever present in the healthy state has been reduced. So same the case with TMT bar. So TMT bar also has there are shifting peaks, and then you can see the increase in amplitude as well. So as the we earlier said, the dark one is the healthy state signal, and each line in between the signals are the each 2 or 4 or 6 are and the the consecutive signals, and the 38th, our last one is the red one. And this one is for the epoxy coated one. So the dark one is the baseline, and the red one is the structural peaks, change in structural peaks, and the amplitude shift in peaks. You can witness it directly. So you can see something in the before slides. You can see that there is the dampening of some peaks. This is dampening of this piece is due to the, we know that in iron when the steel is exposed to salt water, it will undergo some chemical reaction which initiates the which accelerates the corrosion actually in the normal scenario. But here, because we are also even over that, we are maintaining a potential difference so that it can accelerate even more. So this is the iron oxide formation. You can see whatever you are seeing, witnessing here is the iron oxide formation over the TMT bar. This is due to the reaction in that electrochemical cell. So at 26th hour and 38th hour, this increases the this increases the structural weight. So the damping of peaks in the conductance signals has been witnessed. So you can see this iron oxide is nothing but the rust, whichever we see in the any industrial structures or in the steel structures that are in offshores or wherever. You see that is exposed to the moisture content steel or steel exposed to steel structures in the steel bridges in the rivers or near dams like etc. So the after corrosion experiment, you can see here that these are the frustrated rebars and the corroded rebars. This is the cathode bar. After 38 of corrosion, these are the epoxy. You can see left one is the healthy one and the right one is the corroded one. And in the each sample, and the epoxy, there is a no deterioration in the surface, but the bottom portion in the cross section, bottom portion, the epoxy portion has deteriorated. When you are seeing for a plain bar, in the plain bar, the surface has get deteriorated more. This is the plain forged steel, which is highly corrosive resistance. And there is a surface deteriorations. But when you come to TMT, you can see the drastical reduction in the cross section. Cross sectional itself, there is a drastical reduction. So this this happened because the ribs around the TMT bar had given the advantage to the iron oxide to accommodate over easily along its perimeter surface, along its perimeter. So it take process. So there is a accelerated corrosion took place there very in a drastically. Corrosion happened very soon. So after 38 hours of accelerated corrosion, you can check the final mass of the rebars. You can see here. So there's a reduction in masses, whichever we have seen here. You can see, you can witness here very clearly. See, epoxy coated has 11 grams of mass loss, and TMT bar has a 73 grams of mass loss, and plain forged steel has the 13 grams of mass loss. So here you can see that RMSD value. RMSD value is the root mean square deviation. So it is nothing but the mean deviation in the structural peaks of this is taken for the healthy baseline signature to the topmost, that is the damage 38th hour signal. So for this, from this signal to this signal, how much is the deviation in that conductance signal, sir? So that analysis is done through some statistical tools. So in that, yeah, RMSD is the one of those tools where I have chosen. So you can see that, so 75.18% deviation in the TMT bar we have founded. So that's the more corrosion. It is more subject to corrosion. So here it clearly states that epoxy coated steel rebars has better resistance to corrosion more than plain and the TMT. And as we said, for the bare bar steel corrosion, we have seen. Next is for the concrete covered, that is steel bars embedded in the concrete prism, cylindrical prism. So these are the materials I have adapted for the cylindrical prisms, concrete mix, cement 53 grade PPC, and coarse aggregate as usual from 10 to 20 mm, and fine aggregate as a M sand, and steel as we discussed, plain TMT and pre-stressed and epoxy coated. So the pre-stressed one and the again the total monitoring has not discussed till now, but for the plain forged steel, TMT and epoxy coated, as for first 10 days of data, for first 10 days data has been acquired, and those results are discussed here. So as usual, sensors are piezoelectric sensors we used for the bare bar corrosion. So this is the mixed design I have adapted for M to achieve M30, and we casted totally 6 cylinders. So in 3 cylinders with piezoelectric sensors and 3 without piezoelectric sensors. So for destructive testing without piezoelectric sensors, we have casted, and for with piezoelectric sensors, we have casted 3 for the monitoring purpose. And that here also, as in the same way, the whole setup is exposed to the chloride induced chloride environment, that is made possible through adding the sodium chloride laboratory salt at the 3.5% concentration in the water. Here 75% of immersion has been maintained after 28 days of curing. So for the first 10 days, we can see that epoxy embedded RC struct element, that how there is a deviation. It follows the trend very nice, and you can see there is a very small changes in the peaks in the amplitude of the conductance signals day by day. And then again for the TMT, you can see here same for the first 10 days at the frequency of 2 days. So these are the conductance signals, and for the plain embedded. So in this you can see that from the accelerated bar, only bare bar, we can suggest that epoxy coated bars are very more corrosive resistance when compared to plain and steel. Still, we have to continue this project for another 90 days in order to get the when the same rebars has the concrete cover, the time taken to penetrate the chloride ions to take penetration to the concrete, and to that we call as the propagation period. And then when the period starts under initiation period to initiation period is the when those ions go penetrate to the concrete and reaches the steel surface, steel bar, that is the initiation. And then when the corrosion happens, that is the propagation period. And then next then we after concrete will starts to deteriorate, because as we say that the iron oxide formation, it forms the some new material around the surface. It is the expansive reaction. So since it is an expansive reaction, there are some forces that the expansive reaction, because it is tightly compacted, concrete is a dense material. Because of the iron oxide formation, there will be some enlargement, there is a new particles formed inside. It will push the concrete material over outside. So that expansive forces cause the concrete to deteriorate, and even more the quality of the dense concrete, hardened concrete. So these are some of my references I have took from I have gone through. Thank you.